Hello, good afternoon, welcome everyone to the last lecture of the second day of Baltic Summer School of Digital Humanities. And let me welcome our dear guest, Javier de la Rosa, and we are really grateful to him that he made it to here despite the very grave difficulties related to his flight. And Javier de la Rosa is a senior research scientist at the Artificial Intelligence Laboratory at the National Library of Norway. And his lecture maybe is the one that is most at the heart of our focal themes of the summer school, because first of all, he will talk about the implementing of artificial intelligence technologies at the National Library of Norway, and also he knows a lot about training large language models for smaller languages. So welcome and give floor to Javier now, but just to remind you, after the lecture, there will be a questions and answers section, and I will read the answers from the Zoom chat, so welcome to write them already during the talk. And then I will be also passing the microphone in the classroom. So don't start asking questions from your place directly, then wait for me to bring the microphone to you. And now welcome, Javier.
Thank you, Anda. My name is Javier de la Rosa. I work at the AI lab at the National Library of Norway. And today I'll be talking about how we do artificial intelligence in the National Library of Norway, why we do it, with what kind of resources. So a couple of years ago, before the whole ChatGPT storm broke everything we understood by AI, I was invited to deliver a talk into a session called the National Library of the Future. They decided to use this image indeed generated by an AI to illustrate what the National Library of the Future might look like. And I was thinking that this image actually looks a lot like the mountain vault we have built in Norway. This is a vault that we have built to store all the physical objects that we catalog and digitize. After the whole digitization pipelines are done, we store the copies of the physical objects in this vault. What's special about this vault, minus the lasers and the light and the light rays, is that it's built inside a mountain. It's a hollow mountain. We have emptied out a whole mountain in a town close by the polar circle, and then we have filled them up with robotic shelves. These are the kind of shelves that you don't see people operating. There are many aisles and many robots going around, pulling boxes, putting books, moving everything around. So it's kind of, to me, the first time I went to visit this mountain vault was like a sight from the future, at least to me. But how did we get here? How did we get to the point that we needed to actually empty out an entire mountain to fill it with physical objects? Well, the National Library of Norway is kind of young when you compare that to other national libraries out there, like the National Library of Spain or France or the National Library in the UK. Those are like more, in a sense, they are imperial libraries. They have a long tradition of royal ownership of culture. But the National Library of Norway actually is spun off of the University Library of the University of Oslo. It was formally established in 1989 with the mandate to preserve the published information for posterity and give access to all Norwegian citizens to this information. But it wasn't until 2005 when the then director came up with this manifest, that's almost 20 years ago now, in which they basically recognized that if something doesn't exist on the internet, it's almost like it doesn't exist at all. So they concluded that we must digitize the entire collection and make it available to everyone. That was 20 years ago. If we fast forward to now, We have digitized almost 90% of all the books ever printed in Norway. We have more than 80% of all newspapers ever published. We have everything produced by the radio, the radio broadcast entities we have. We run our own continuous harvest of the internet. We now have like petabytes of information crawled by ourselves in our own infrastructure. And we have much more. We have photo, film, magazine, maps, manuscripts, letters. We have almost everything. And everything is being digitized. The problem with this level of mass digitization is, what are we doing about it? What can we do with all of this? We have not petabytes of data, but it's really hard to facilitate the finding of information in this sea of data that we are providing now. So one of the initiatives that the National Library of Norway decided to take on was the creation of the AI lab, the Artificial Intelligence Lab. The lab was founded like 6, maybe 7 years ago, with the idea to be able to make all these collections actionable and easy to discover for the patrons of the library. So we have a very large and varied digital collection, and the lab doesn't only contribute to make all of this more discoverable, but also contributes with knowledge about AI, both internally in our own pipelines and day-to-day work, but also externally. We sometimes deliver workshops to people in the library, to other institutions. If there is anything related to AI, we are somehow involved in those initiatives. But we are very few people. We're only 4 full-time people. There is the possibility of something that we call a researcher in residence, like a visiting scholar, but for the AI lab, we right now have 1 person in this role who is working remotely most of the time, and then we're looking to increase the team, because 4 people is definitely not enough as you get to work with AI. So where are we located? So the main headquarters is in Oslo. That's where all the public-facing buildings are. We have a beautiful building that dates back to the years of the University of Oslo. And then the core IT AI lab activities happen in Mo i Rana, which is the city close to the polar circle. And then we have some researchers from Tromsø who live in Tromsø, and then myself, who comes and lives actually in Madrid. I live in Madrid and I work for the National Library. This is kind of a funny story. The whole thing started during the pandemic. I was hired to work at the AI lab, but because of COVID, it was really difficult for me to travel and settle in the north of the country. So I stayed in Madrid until the whole thing passed, but it actually never passed, so it really took a long time. So they made it work for me to work fully remote. And after it was actually possible for me to move up there, it was not really necessary anymore. So I live in Madrid, but I work for the National Library of Norway. What is it that we deliver? Well, we try to create training data sets based on our own collections, but we also fully train models. It's not only the pre-trained, I will explain in a second the difference between pre-trained and foundational models and fine-tuning and all of that, but we try to do a little bit of everything, because when we started the lab, all of these technologies were suited for English. So when you try to apply them to your own specific language, you soon find out that they are not really performing as well as you would expect. So on top of these models that we custom create, we sometimes build services or APIs for others to use. There is also a digital humanities lab in the National Library that uses some of our APIs as well. For example, the name entity recognition API that we have built on top of a fine-tuned model of a foundation model that we build ourselves, which is called MBBERT. We're also trying to support internal workflows. An example of this could be the work that we do with the Sami bibliographers. They right now have like a very physical workflow in which the bibliographers go physically to the building, take a bunch of books, and then they manually take a look at the content, and then they decide if it's okay for those books to be part of the SAMI bibliography. So we took an AI spin on it and then went over all the material that they had already collected and created a model to suggest which books might be relevant for the SAMI bibliographers. Those are the kind of things that we internally do. We also do a lot of experiments, pilots, demonstrators, and basic research. And I want to highlight the word experiments, because that's where we spend most of the time doing experimentation. The AI lab is a very privileged place because we are allowed to fail. And it's this failure that allows us to go forward. I won't say that 90% of what we do is a failure, but it's a high percentage, and we're allowed to do that. It's a way to actually keep improving things. And we have this safe space in which to actually do all this kind of experimentation. But how do we do all of this? What is actually involved? What are the bits and balls of all of this that I'm talking about? Well, it all started with counting words in sentences. For the more DH-oriented folks in here, they all know that by counting words in a sentence, you can really get a lot of things done. If we go to the definitions, for those that are more at the theory level, a language model is just a probabilistic model of a natural language. And a probabilistic model is just a description using math. So a language model is just a description using math of a natural language. That's all it is. And by mathematical description, we mean a lot of different things. For example, if we have a chunk of text, in this case it's just like a review of a movie, I can get all those movies assorted. We lose the order in which they are actually written in the sentences, and then we get a bag of words. If we take only the unique words in this bag, we get a list of all the unique words in the bag. So if we count how many times each of the words in the bag appear, then we get what is called the bag of words technique. When you apply this technique to a whole corpora, you can start to doing analysis on the content, not on the metadata, not on the titles, not on the authors, but on the actual content. And this is very widely used, for example, in the field of stylometry. This is a language model. It's not a language model as advanced as BERT or ChatGPT or Gemini, whatever, but it is still a language model because it's describing language using math. And it's a very powerful representation of the text, because once you take all of this information and try to plot it, for example, let's say that I only going to consider the 3 most frequent words in the whole list of unique words. When you plot that, what you get now is a vector space model. And then you can embed the representation for each of your documents in this space, which allows you to do mathematical and mathematical operations using vectors, using numbers on the actual content of the book, which was a kind of a revolution at the time. So with this approach, we just really counting, we create this vector space model that allows us to operate on a vector space, which is very abstract, but at this point, we all know which of those numbers means. Each of those numbers actually mean the number of times this word appears in a document. So that allows us to do classification. For example, stylometry, general classification, or things like that. But this representation is very bad for a couple of reasons. The first one is sparsity. When you have a big enough corpora, there are a lot of words that appear only a few times, and there is a bunch of words that appear a lot of times. That's just, that's just by the very nature of language. There is an experimental law called the CFLA, And then you will see that there are a few words that appear a lot, and then there are other words that appear fewer and fewer times. So the result in this vector space representation is that a lot of these numbers are going to be zero or very low quantities. And the other problem with this is semantics. This is not really capturing the semantics of the books. It's not really capturing what's being said. It's more about how it's being said. So in order to overcome these limitations, around 12 years ago, a researcher from Mikolov was from Stanford, I think, and relying on the distributional hypothesis, came up with a thing called word-to-vec. Word-to-vec is still a representation. By representation, I mean just a list of numbers. So it's a way of representing words using list of numbers or vectors. And the core of this idea is the distributional hypothesis, which says that words that occur in the same context tend to have similar meanings. Now we are delving into the meaning world, not just about how things are said, but also what they actually mean. If we rephrase this distributional hypothesis, we can say that a word is characterized by the company it keeps. And both of these formulations have been in the literature for decades. But it wasn't until 10 years ago that someone had the idea to actually put them into play. The way word-to-vec works is by training a neural network model. I'm not going to go much into the detail of how actual neural networks are trained, but I will explain what are their objectives. The objective of the training of a neural network is what the neural network is trying to solve, right? We know that GPT tried to solve the problem of predicting a word given a few words that came before. BERT has a different objective. Models like T5 have different objectives. ASR models like Whisper have different objectives. So the objective of word-to-vec models, in this case, was trying to predict a word given a context. But this context is assorted. There is no order here. So for example, let's say that I have a couple of words, victory and brave, and I'm only considering a vocabulary of 500,000 words. I have a huge corpora, but I'm only taking into account 500,000 words. Not 100, not 12, 500,000. And then I have a neural network, which is in the case of word-to-vec, is a very shallow neural network. It doesn't have a lot of different layers. It just has only one hidden layer. That's what we call it, a hidden layer, because that's the one that we don't use. We have control over the input, and then we have the results on the output. But what these people realize is that when you're trying to learn, when you're trying to force the model to learn what word comes given a context, in this example, maybe I can have the vector for victory and the vector for brave, and I want to know, using a context of one to the right and one to the left, what word might come in the middle. We get the neural network to learn that maybe one of the words might be first, and then it will give you a probability. Another word might be winner, and it gives you a probability. But what is really interesting here is that instead of focusing on the actual results and the predictions of the network, they focus on the hidden layer, the internal representation that the neural network built in order to make its decisions. And when you plot that, you are now losing the semantics of the vectors. You cannot say that, for example, these columns is representing the number of times that this word appear in the corpora. The individual numbers in these vectors don't have meaning by themselves, but they allow you to do trigonometrical operations among them. For example, when you have the vector for the word queen and the vector for the word king, and then you plot those in a space, and then you also plot the representation of the word man and the representation for the word women, you can see that the relationships are proportional. the meaning is being transferred in this space because it is somehow encoding the semantics, not only how things are said. The same thing happened with semantic families, for example, capitals and countries. If you plot all the vectors representing capitals and all the vectors representing countries, you will see that there is a relationship between the distances between all those vectors. The same thing happened with, for example, flexions of verbs. So suddenly, we have a space that is also a vector space, but in which mathematical operations have semantic meaning. If you do operations in this space, you are doing operations with the semantics of the text. How this actually look like in real life is more like this. It's not so clear, so to speak. But for example, if I have a vector representing king, which is a bunch of numbers, and then I subtract the vector representing man, and then I add the vector representing woman, what I have as a result is something that is very, very similar to the vector representing queen. So in a sense, when I subtract man, I subtract the manness in king, and then I add the womanness in woman. So what I have at the end is queen. And this is the very reason language models are biased machines. This is the kind of information they encode. If in your corpora from the 19th century, all the doctors were men and all the nurses were women, these numbers are going to reflect that. That's just the way it is. Try to unbias language models is very difficult because these biases, these machines are designed to exploit those biases by definition. So now we have solved the sparsity problem because all the elements in the vectors have some sort of meaning. We have also solved the semantics. We have also solved the similarity issue. Now we have a way to find similar words and relationships between them, but we don't have document level. And more importantly, we don't have polysemy. If I have the word, the vector, the representation for the word school, I don't know if I'm referring to the kids go to school or a school of fish. They are written exactly the same way, but they have very different meanings. So I'm losing polysemy because there is only one single representation for all of these words, unically, sorry for that. But what about the document level? At the beginning, when we had the bag of words, it was very natural to think at the document level. You encode documents, you get some sort of representation, you can do operations with this. You can find the anonymous author of a book, you can find the genre, the style, and all sorts of things. So a natural extension of word2vec is to train these models not only to predict one single word, give it a context, but one single chunk of text by any arbitrary definition of chunk. The chunk can be a sentence, a paragraph, or an entire book. So you can now train using the same foundation, the same ideas. You can train models that are going to give you numerical representations for book-length documents. Each of these representations contain values that embed the document. That's what we call the document embeddings. Embeddings are going to be close to each other when the documents are semantically similar, but there isn't a single definition of semantically similar. So it's really going to depend on your corpus. We had done an experiment like this. For example, let's imagine that we put 2 axes and then we plot all of these vectors. So if our models is working fine, we should expect that, for example, all the Harry Potter books are going to be grouped together, which in the jargon is called clustering together, because the similarities between all of them together is going to be very close to each other. They are clustering together. And we can use these clusters to find books that are also similar to the Harry Potter series, even if they are not written by J.K. Rowling, or even if they are not the same kind of fiction. But they're going to be clustered together, and using that kind of jumps in the vector space, you automatically have a recommender system. You have a recommending machine. You give it a book, it gets the numerical representation, and then you can find which other book in your collection is similar to the one you have given as a query. That is what we did. So given an object, it doesn't matter if it's a book or an image, it also works with images in a slightly different way, but at the end you also get a numerical representation. So we can get the numerical representation of that book using the word-to-vec or doc-to-vec or back-of-word, whatever of the language models techniques we have seen before. So what you have to do now is compare that numerical representation against the numerical representation of all the other books in your collection. And then you have to establish some sort of distance metric, like, okay, I have a couple of vectors, a couple of lists of numbers, and I want to know if they are close to each other. So I define a distance metric. Excuse me. One of those distance metrics could be, for example, the cosine similarity. If you plot these vectors into the vector space that I showed before, you see that they are like arrows like this. So if the angle between those arrows is very small, that means that they are very similar. So I'm going to use that as my distance metric. And then when I rank all of these elements by the distance metric, I get all the results. And we have implemented this already at the National Library of Norway in a project that is called Maken. It's actually publicly available. It's been in production for a couple of years now. We did a one-off processing of the entire collection as a pilot. It worked really great. People were very interested. We ran user studies. We designed personas, and then we did user interviews, and then we did interviews with actual people. They really liked the system. They liked the serendipity of the system, like you go to the system looking for something, and then you get out of the system with something else that you were not thinking about. So they really liked that. And it looks very simple, because we think that the most successful deployment of AI is AI that is invisible. When they're using AI, even without realizing they're using it. So the interface looks like this. You can look for a book or an image, or you can select the ones we have already pre-selected for them, and then you click on one of those, and then automatically you will see a bunch of results. And then it's very addictive, because you click on another result, and you get another list of related items. And this is all based on all the things I have explained before. But we still have the problem of polysemy and language understanding. Now we can get similar items, we can plop them in a space, we can get recommender systems, we can actually deploy a system that gets updated every week. That's the one we have right now. But we are not solving the polysemy problem at the word level, and we are not really understanding what the language is. I cannot ask questions about paragraphs or complete books. To solve that, excuse me, to solve that, the researchers from Google and people from Silicon Valley, mostly, came up with this thing called Elmo. If you've been following the whole BERT thing, there was a time in which every research paper was using a, what's it called, the Sesame Street character names to name everything they were doing. So there is Elmo, there is also Oscar, there is also Bear, there is also all of them. So the way it works, the Elmo embeddings, as they call it, is that they have a list of words, and they want to create a different representation of the word depending on the context. Again, this is very similar to the same idea that they use in the word-to-vec original network. So, but this time, I want the representation to be different if the way in which the word is being used is also different. For example, let's stick to improvisation in this skit. has a very different definition of the word stick as a verb. But if I say I was walking down the street and I grab a stick, that's a different kind of a stick. So I want that representation to be different in order to grasp the meaning of the words. The way they did this is by applying the now famous language modeling objective of the next word prediction. So given a word or two or three, I want to condition the probability of this model to predict a word given the ones that have passed to the model. I won't get into the mathematical way of explaining this because it's very confusing, but as you go forward, as you add more and more words to this prompt, you're going to get different words at the other end, because you are conditioning the word that the model is looking through his internal state in order to fulfill the probability of the words that are already given to you. That's the next word prediction objective of the language models, which are actually also neural networks. But the Elmo researchers also introduced something that was not used at the time. They introduced reusable components. So they had developed this idea of neural networks stacking up a kind of layer called long short-term memory layers. They stack a few of them, and then they realized that they could actually use that network, train it once, and then reuse it somewhere else. That's the beginning of the fine-tuning technique, right? And they also use, for the very first time, a very massive data set. They were the very first to introduce all of these techniques. So now we have in context embeddings, that is, embeddings that change depending on the context. We also have, at the same time, around the same year, the attention mechanism, which is something that Google researchers introduced. It looks like this, which is absolutely terrifying, but it's easy to understand. This is called a self-attention matrix. Internally, what all of these attention mechanisms do is to give weight between the words of a single sentence to somehow signify how much attention each of these words should pay to the others. So, for example, I have the same word in the rows and the same words in the columns. A fluffy blue creature roam the verdant forest. So by using some, I don't want to say black magic, but by using some very deep mathematical definitions here, they are able to train the model so each of these words assign a higher score to the words they are attending to. And this attending to means that these relationships should somehow be weighted higher than the others. This is the whole foundation of every single language model today, the attention mechanism. Before we have this attention mechanism, we have two different sentences. Because the first people that designed this were using these techniques to do translation. When you do translation, you have one language in the rows and one language in the columns. And you cannot do translation literally word by word. It's really not a very good approach. But you need to know which word is attending to which other words. Because in some languages, the articles might come up the end, or they use verbs differently, or they don't have gendered nouns, whatever. But they flip that whole idea and define this self-attention, how the sentence attends to itself. And this is the core piece that was missing for the pre-trained language models. Then the ULM fit by the people from fast.ai introduced the notion of the pre-trained models more formally. You train the model once on a huge corpus, and then you adapt it to something else that is called the downstream task. And you can use it for whatever, in entity recognition, classification, part-of-speech tagging, whatever you need. And that's basically how the first GPT came ever to be. Those are the three ingredients that made the first GPT, GPT-1, the first transformer model released by OpenAI. This model is what they call an autoregressive model because it is only a decoder. It's trained on the next word prediction task as an objective, and it's only able to produce words at the end. But this is the beginning, right? So they were not really interested in making the model speak. They were not really interested into having conversations with the model. They actually didn't know the models were capable of doing that. So what they did is they stuck these transformer blocks with all of these attention mechanisms and whatnot, and then add an extra layer at the end. If you think about the neural network, you have the whole thing, and then you add a layer at the end. So if you're doing classification, you add a linear classification head. If you're doing entailment, you add a linear entailment head. If you add question and answering, you add more linear layers at the end. So it was very powerful in a sense, but it's not what we know about today. We now know that all of this information is already encoded in the models. So there are other ways to elicit that knowledge from the network without the need to add in more layers at the end. Then enters BERT. BERT took exactly the same building blocks, but changed the objective, right? It's called bidirectional encoder representation from transformer, which is basically using exactly the same ideas, the same blocks, but instead of being the coder, just producing words, BERT is an encoder. It takes words and produces a vector. This is more similar to what we had seen at the time. Given a chunk of text, it produces a vector representation of the text that you can operate with. So they did this by not using the next word prediction. They use a thing called the masked language modeling. And the way it works is by self-training the model. So you give it a text, and then it randomly masks out a few words in there, and because you know the ground truth, you know what those masked out words need to be. So you train the model to predict those words. That's how you get the representation of these models. And it was a revolution. It was a revolution because then you can start fine-tuning. For some reason, BERT became more famous than the GPT-1. It's exactly the same technology, using in a slightly different way, but you also had to train a big model first on a massive corpora and then add layers to do the fine-tuning. So what kind of task can BERT tackle? Anything related or anything that can be reformulated as classification. Anything at the word level, or the token as we call it, or the sentence level, the sequence. So, okay, we thought, this is very nice, so let's just see how these models, or the multilingual versions of these models, work for the Norwegian languages. In Norwegian, we have two official written languages, which is Bokmål and Nynorsk. The models were not doing very good. So we saw that for English, it was very impressive, and when we used even the multilingual version of these models on our own languages, we found out that they were not doing a very good job. So we decided, okay, how hard can it be to build our own BERT model, right? It only costed them a few $1 million to build. Can we actually build a model that is as powerful for Norwegian as BERT is for English? So we started to analyze all the work that they have done. We started to analyze all the models, all the frameworks they use for training, all the infrastructure, all the code, and all the training data. And this is based on a very, very heavy technological environment. 5 years ago, only a few people had access to this kind of environment. We were lucky enough to be sponsored by Google itself to borrow some of the resources, which is called the TPU Research Cloud. But actually, today, anyone can apply for this kind of funds. And they will give you a lot of resources to do the training, no strings attached. But at the time, it wasn't that common. It's called the TPU Research Cloud. It's called the Tensor Research Cloud these days, I think. So now we had some sort of technological framework, and we had the library collections. We wanted to use our collection to build a model for Norwegian. So we defined a project, which is called the Norwegian Transformer Model, so with two tasks. First, build a big corpus, and second, build the first and best Norwegian transformer model. That's how the MB-BERT came to be. If we look back at the kind of data that has been used for training these models, for example, the first BERT used roughly 300 megabytes of text from the Encyclopedia Britannica, and then the Roberta models and the multilingual BERT only contain around 1 gigabyte of Norwegian text. The English BERT was trained on 16 gigabytes. So it was actually pretty obvious that the amount of text was a key factor in here. So size matters. It matters a lot. But we very soon discovered that quality matters even more. It's not only about dropping everything that you have in a region and trying the model to perform very well. You need to do a lot of curation, a lot of selection, a lot of rejection of the documents, a lot of carefully re-OCR and things that were scanned like 16 years ago, because OCR, it only gets better and better. So as our own process went along, we discovered that if you outline the 3 main phases in order to train these models. So we have dataset creation, which includes curation, selection, and cleaning, and then you have pre-processing for data mixture and tokenization, and then you have training, which is the actual nitty-gritty details like learning rate, optimizer, things like that. So we soon discovered that as the technology advances, it's becoming more and more important to spend your time in the dataset creation phase. It's going to be a key factor how good your data is, how much the model can learn from, and how clean the data is to get a very good performing model. So we resorted to our own collection at the National Library of Norway. We have books, newspaper, public publications. We have Lovdata, which is documents from the law in Norway. But we also had other agreements, and we also have Common Crawl, which are publicly available dumps of the whole internet. So we use those, extract the Norwegian part of it, and then put all together to create a massive data set. I'll go through this real quick. So at the time when we released our model, Facebook has already released a model called Roberta, which was trained on 10 times as much data as the first English BERT. So we were able to get to 190 gigabytes of data. I'm using here gigabytes because I don't have the numbers for actual words. The token numbers really depend on the tokenizer we're using. So gigabytes is not maybe the best proxy, but you kind of get the idea. So this is how the Norwegian colossal corpus, as we call it, looks like. So most of it is composed of newspapers. Then we have Malfrid, which is the public administration documents, and then we have the parliament documents, and then we have the books. This is the part that is copyright free, that we can release to the public and that we can share. But there is also another version of this corpus, including all the protected materials that we had under copyright, all the web, all the agreements that we had that we cannot share, that was almost 3 times as big as the data that we could actually release publicly. It was not easy to decide whether we could even publicly release a model trained on these materials, because they are protected. So we did not. We released the model trained on the parts that were publicly available. So we say, okay, let's now put to the same test the model we have created to see how well it's doing. And it turns out that the model was very, very good, much better than multilingual BERT for English, but for Norwegian. It was actually very good for English, good enough, very good for Swedish, and actually it was better at Danish than the Danish models that they had created. So they got pissed about that, so they decided to actually create their own institute and everything to beat our models for Norwegian. That was beating their models for Danish. So on top of this, we built a lot of different variations. We created models for name-entity recognition, sentence embeddings, which are a variation of the model that allows you to say if 2 sentences are saying basically the same. We also have textual entailment, which is a way of saying if 2 sentences are, if one is the conclusion of the of the other one. For example, for name entity recognition, we have this sentence in Norwegian, Peridag har Peridag startet firmaet Peridag. You will see that there is per and dag 3 different times, but they have very different meanings. In one is just a person name, in the one is a company, and in the other one they are just adverbs, I think. And dag is also the A. So we created a model for that to facilitate text analysis, and now another researchers are using this model to do their own NER analysis. But what about generation? I have talked about encoder models, a little bit about decoder models, but these days everything is about generation, right? So to fully understand what generation is and why it's important, we need to think about how these models are actually built. So BERT models, encoder-only models, and T5 model, sequence-to-sequence models, are first trained with one objective, either spam corruption like T5 or mass language modeling like BERT, and then they are fine-tuned for a specific task. That fine-tuning is less costly than pre-training the whole model, but it's still a way of further training the model. Now, if you look at autoregressive modeling like GPT, for pre-training, you use next word prediction as an objective. That's how you get foundational models. But for fine-tuning, you use exactly the same, next word prediction objective. So they found a way to get rid of the whole fine-tuning phase, because it's exactly the same objective. You're just training with more data, more specialized data, but you do exactly the same. You don't have to keep adding layers and removing them and putting this in a downstream task. It's the same model, but now it can perform many different tasks. So this was it was a time saver, both in money and time. And since 2018, GPT has been evolving like a lot. We got GPT-2, which was very dangerous. It was so dangerous that they could not release it publicly. Maybe you remember that. They had a public statement saying that we cannot release this technology. It's going to break havoc in humanity. But still, they released GPT-3 or something very close to GPT-3, and then ChatGPT came into the scene, revolutionized everything. A few months later, they released GPT-4. It's all the same technology underneath. It's all next word prediction. They just added something called alignment to make this model be able to maintain conversations, but it's all the same thing. After GPT was published and BERT was published, there was a whole revolution of companies, private companies and research institutions trying to come up with their own models. They used slightly different variations in the architecture, slightly different variations in the way these networks were trained, but they all released models, most of them publicly available. You see that the yellow ones are publicly available. So it was really a revolution. The problem with this revolution is that it also became a rat race. Everyone was pushing to have the best model out there, the fastest. The problem with this kind of way of working is that only the most profitable companies have enough people, enough money, and enough resources to do so. So after a period of time, everything basically crystallized into GPT-like models. It's hard to hear any more models or papers talking about BERT or sequence-to-sequence models for text. Now, these days, it's all about GPT. We create our own GPT model as well, based on the corpus that we use to build the MBBERT model that beat the English and the Danish models. And we train it on the same infrastructure, but now we are talking about a model that is how many times? So BERT was 300 million parameters, and this is 6 billion parameters. It's extremely big. It's really hard to imagine how many numbers this model have to handle in every single interaction you have. And this is 25 times smaller than the GPT-3 model is. So ChatGPT is probably 1,000 times bigger than the model we released. It took us a year to train this model. We had some resources, we have the corpus, which was already very good, so we just left the machine running for a year. After the year, we took a look and we released the version 1. It was a good model, it had some problems because it was fixating a lot on all Norwegian, so we trained a version 2 on top of that. It took another year to train this. So it was becoming very, very hard for us to justify the cost of training these models when OpenAI and Google were releasing models every week, basically, right? But we got good feedback from these models. There is a newspapers company that was analyzing these models to be able to generate the titles of the news articles in their newspaper. So we're using these models, doing an extra round of training, and then trying to create a title generator. So they tested a few models, and then they told us that the model that we had released was actually the better performing one. So that's something that we really took into consideration and kept working on that. Around that time, Llama or Llama was released. What is really interesting about the Llama family of models is a small thing called Alpaca. Alpaca is the smaller cousin of the Llamas, for those of you that don't know. But what they did was that they used a specifically crafted prompt against ChatGPT. With those prompts were basically questions. And then they say, OK, ChatGPT, given this question, please generate 100 questions that look like this. And they did that 2,000 times. And then they ended up with a data set of questions and answers of about 52,000 entries. And then they trained Llama on that. And then they realized that the model was already good enough to answer questions and almost have a conversation. So that was another revolution in here. There's tons of revolutions in NLP, as you can see. And then people started to experiment with different ways of crafting the seeds, crafting the prompts. The prompt engineers came to be. Some people actually got the prompt engineer title in their CVs. I don't know what that really means, but that's what they do. So we did, OK, let's do an experiment. And it was true. We did an experiment in Norwegian, and it was actually true. We got our GPT model, training on a Norwegian set, translated from Alpaca, and the model was able to answer questions. So a model that is 1,000 times smaller than the one you use every day in ChatGPT is already able to answer your questions, with some caveats, right? This is not a factual model. It's incapable of giving you factual information. So you really need to be aware of what you're using, where all of this technology comes from. It all comes from the data it's being trained. That's it, no more than that. And one of the problems we had at the library is about the context. The context is a notion of how many words can you fit in that terrifying black matrix I showed at the beginning, right? The bigger the matrix, the more words you can fit into the model at once, but the bigger the matrix, the most costly the inference of this model is, because it takes more time to process, it takes more memory, it requires bigger machines. So we decided to take a look at our own collection and plot all the lengths, and histogram with all the lengths in our collection. To make a distinction between words and tokens. Tokens are just, a token can be a full word, but most of the time a token is just a subword. It's a small part of the word. So when you say that a model is able to handle 1,000 tokens, that's always less or at least equal than 1,000 words. So after we plotted all of that, our MBBER was only processing that tiny bit of our collection, because the context length in BERT is usually 512. Our GPT model was designed with a context length of 2,000 words. So only that tiny part. So 99% of our books won't fit in our own models entirely, right? So we look for options, how to fix that, and we discovered that the technology was not mature enough. Not even GPT-4 Turbo was able to process our whole collection, not even Claude 2.1. Maybe now with the new Gemini, with 1 million tokens, maybe we can process entire books. But we are not there yet at the infrastructure level to train models that are able to digest in a single turn 1 million tokens. That's just insane, the cost of doing that. But we also have some work in other modalities. For example, for speech-to-text. We have a good collection of radio broadcast. And we thought that maybe by having this technology, we could turn all of these speeches into subtitles that you can actually attach to the videos that you can download. And you can do further analysis on using the very technologies we developed at the beginning. You can find entities in the spoken audio of these speeches by combining both the ASR, automatic speech recognition, and the models that we had. So we experimented a lot with a technology called BIBLIOTÄKA, which is a model that tries to create acoustic representations of audio. It works in the way that BERT works. It creates a representation of the audio, and then you have to fine-tune it to do some other tasks. For example, you can fine-tune it to do ASR, you can fine-tune it to do speaker diarization, you can fine-tune it to do other different tasks related to audio. I'm gonna go over this real quick. The problem with this is that it took a lot of iterations, and we have to build the data sets ourselves. So we use the Norwegian Parliament speech corpus, which was created by other colleagues at the library, and then we use those interventions in the Parliament properly transcribed to train these models, and then we fine-tune it on the very same data. And we got very good results, but this is a very verbatim representation. It's all lowercase, is actually spelling out words, it doesn't have commas or colons or any sort of punctuation. It doesn't tell you when one person is speaking or the other one is speaking. It doesn't use capitalization. It was a very raw way of transcribing. And then OpenAI released a thing called Whisper, which instead of being trained on properly crafted, manually detailed transcription from linguists, they just used YouTube subtitles. And it worked incredibly well. It worked so well, even for Norwegian, that we had to adapt it ourselves. So what we did is we took the corpora that we collected for training the BIBLIOTÄKA models and then did our own training on Whisper. And then we compare. And then we even went a little bit further and talked to some of the researchers working with the Sami community in Norway, because there was no support for Sami. Sami is an indigenous language spoken in the northern part of Scandinavia, which includes Norway, Sweden, Finland, and a bit of Russia. But in Norway, there is only North Sami, South Sami, and Lule Sami. So we have to provide language technology for their community as well. But Sami is spoken by a very few number of people. So collecting data for Sami language technology is very hard. So we thought that maybe we could adapt first a model from Whisper to Norwegian, and then from Norwegian to Sami. And let's see how that was actually working. But the problem is that at the time, we didn't have a good performing model for Norwegian. So we took Finnish, because when we ask the Whisper model to transcribe audio from Sami, it usually mistreated that language as Finnish. So we thought maybe here is the kind of angle that we can use to further train Whisper on Sami. And it worked incredibly well. People actually got very excited, and we now have a longer research collaboration with them. We are developing further this technology, making the models publicly available, training in larger clusters, because it seems that for them, text models were not very exciting. They really don't need text models, but being able to transcribe their ancestors' speech was more important than actually being able to ask questions to a machine in text form. These are a few examples. We also have some models for handwritten text recognition. I won't get into the details of how we do the newspaper bundling thing because I want to go, sorry for fast forwarding here, but I want to speak about other things. Yeah, I'm sorry, I prepared a lot of slides for the presentation. I'll be very brief, and I'll talk about now the Mimir project. So we've been working in the AI lab for 5 years now, myself for almost 5 years. We were able to put the National Library on the map of AI using all of these developments that I have shown before. Some of them were used internally, some of them were used externally, which is actually even more important because we're now creating resources for the whole society. So in November, at some point, in November of 2023, the Right Holders Organization of Norway demanded compensation to the government for the use of their materials in the training of language models. But the government's response was, okay, let's command a data-driven report in which we can assess how important copyrighted material actually is for the performance of language models. So in January 2024, a consortium was born, led by the National Library of Norway, in collaboration with the University of Oslo and the NTNU, which is the technological university in Norway. And we only had 6 months from the ideation phase to the actual report writing. So we decided, okay, let's get to the task. We created a new corpus, partially based on the one we use for MBBERS. We decided to train 17 different models with different ablations on the data, including, for example, just fiction, including factual sources like newspapers and nonfiction books, including nonfiction, different ablations on the data, just to try to assess how important all of this data is when you are actually using language models. So these are some of the ablations. You see we have the base data set, which is the things that we can share. We have extended, which includes everything that is under copyright or protected. And then we have different ablations. We have what we can share plus newspapers, what we can share plus newspaper plus all nonfiction, only the fiction, all the books, only the nonfiction, all the translated, the non-translated, different ablations here. And then we trained 17 models using different infrastructures here. And we came up with a new way of doing benchmarking because benchmarking suites only work for English. When you're using Norwegian, they did not exist for generative text, only for encoder-only models like BER. So we have to develop in 6 months not only the data and the models, but also the benchmarking suite. So we defined like 9 different type of tasks and then included different data sets in those. And then we discovered that, for example, including copyrighted material was actually making the models perform better. But that the inclusion of fiction was not adding that much of a gain to the language models. Now our job is done, and then the higher-ups need to take this information with the Right Holders Organization in order to decide a proper compensation scheme if we are to use their copyrighted material in the future training of Norwegian books. That's what I will say about this. So to conclude, I have thousands of slides detailing all of this, so if you have any questions, I'll be happy to take them. But what are the benefits of all of this? Well, obvious. There is better access to content for more people. There is more possibilities of use and reuse. We're not only releasing new tools, but also the foundation models that we create that are all public. Even the model that we use for the book recommendation is all publicly free. So we're all contributing to society. so we think, but there are not so obvious benefits as well. So we are trying to put more focus on the content rather than the metadata, because in the end, the content might guide the metadata we use. There are some frictions in the way in which we might include this information, because it's AI generated, and we don't trust it, but even people also make mistakes, so we need to find a framework to make all this work together. And of course, we are trying to change the way our collection is seen and is used. And we're trying to provide all the digital tools, of course, that are the result of all of this development. So thank you.
Thank you. I have many questions, but I first look for questions from the audience. So please raise your hand. It's coming.
Thank you so much for your presentation. I have two parts to my question. It goes back to Sami languages. Are you cooperating, for example, with other Scandinavian countries to develop your research strand on Sami languages? Because, I mean, Samis are living, across, Finland, Sweden. So are you cooperating or maybe competing like you did with the Danes and where you're better? And the second is, according to you, what is that unique angle that is delivered by a research inquiry and technological advancement into these small languages, as compared to to some of the wide-spoken languages, English, etc. Thank you.
Yes. So the first question is about if we are aware of other countries' efforts into Sami, and the answer is yes. Actually. Spanning from the work we have done with ASR for Sami, that got the attention of other communities working with Sami as well. So there is now like a working group that includes people from Sweden, from Finland, and from Norway. We meet regularly every other month, and we just share resources, findings, models, approaches, and things like that. So I would say that that's becoming very relevant. We are, of course, competing as institutions, that's for obvious reasons, but we're also sharing and collaborating a lot. There is actually now the possibility of training very big models by the Finnish, because they have access to a supercomputer called Lumi, which is physically located in Finland, so they can use all the resources for training big models. The problem is that for Sami, there are a lot of resources. So we need to find different strategies, like adapting existing models for which their linguistic structure is closer to the Sami languages. And they're also very different among themselves. One person speaking Lule might not know anything about other Sami languages in other parts of the region. And the second question, sorry, was? Yes.
Whether there are any unique traits that you have identified that you have not come across so easily in bigger languages like Norwegian and English, etc. Thank you.
Yes, that's very, very relevant. I think that it was a bit shocking to me when I came to work for the National Library of Norway, and everyone was super excited about this language technology, right? And it was kind of easy in a way. So they knew that the technology worked for English, so they wanted to adapt it to Norwegian, right? But not for the Sami community, right? They're not as excited about language technology as, for example, other Norwegians are. And that's because they don't see the value directly out of this technology. For example, we propose in a project that I started to replicate the BERT model for Sami using something called the Free Corpus, which is a corpus developed by the Arctic University in Tromsø about all text written in Northern Sami, which is the population with more people in Norway at least. And they said, no, We don't need that. Yes, you can do it. We haven't asked for it. We don't need it. We don't have a use for that. What we really need is ASR, because we want to be able to transcribe. We have recordings. We have the Sami Parliament, the Sami Tinga, with sessions every other month. We want to be able to transcribe that and relieve of the weight of the native speakers doing now that work. So I think that it was a reality check for me, because in languages like in Norwegian, you kind of know what you have to do. But for lower resource languages, you have to listen to the community, because you might end up developing something that no one really wants or needs.
Hello, thank you for your lecture. You mentioned several times sentiment analysis, so can you probably place it into the topic of developing AI, where we are, what is the status quo, at least from your point of view, and also where it will go?
Personally, I'm not very fond of sentiment analysis. I think it's a rather impossible task to solve, because you gotta have a very formal definition of what you are considering to be positive, negative, or neutral. That's also context dependent. It depends also on the literature tradition. My training is as a philologist originally, so trying to know what the text is saying by itself without all the paratext and the context in which the writing was done, the age, the period, the author, the situation in the country, the economy in the country, it's really, really hard. Sentiment analysis works for Amazon. It works very well, because people are very vocal. When they are not happy with something, they swear in the comments. When they are very happy, they say nice things, using words that are really hard to misinterpret. So I think that's one, I wouldn't say misuse of the technology into other fields like digital humanities, but I think that is harder to solve in the digital humanities than it is in the broader NLP context. For Norwegian, for example, I have one comment here. There is a couple of data sets, but they are word-based, right? If you just count the positive words, you will get a sentiment. So you don't really need very advanced technology to do sentiment analysis with the resources we have in Norway, which is not the same as for English. For example, things like the negation and things like that, metaphorical language, they are really, really hard.
Yeah, thank you for your interesting presentation. I have a question about future improvements. So for Norwegian, you said that you included 80 or 90% of all written records into your models, and also web sources. And for the very popular GPT models, they also scraped the whole web, so to speak. So I'm wondering, where will future improvement come from if everything has already, nearly everything has already been included? And will it maybe come from a different model architecture that none of us know so far?
Yeah, where's the whole thing headed, right? Especially for low resource languages or smaller languages. I think that is very important for people working with languages like Norwegian to realize that we will never be in a situation like people speaking English is. They have trillions and trillions of words in their data sets. There are just not enough words written in Norwegian to even match a fraction of that. That's the reality of it. We have scanned almost everything that there is in Norwegian, and all we got was like 300 billion words. That's a third of one of the trillions people use these days for academic models, right? The models they train and then they throw away. For the real models, we're not even there yet, and we will never be. So the options we are considering now are two, is doing an even deeper analysis of the content we have, trying to select documents that are better for the model, that the model learns better from, and also in the creation of synthetic data, like the alpaca thing that I mentioned at the beginning. That's one way of reusing models that are existing already to create more data to feed back these models. Or maybe things like ASR. We have the whole re-archive collection that is an untapped source, right? Because it's not in text form.
Thank you for telling the complex story in a simple, comprehensible way for humanists. So my question is about humanists indeed. And you mentioned you are a philologist also by education, if I understood correctly. Yep. So we, as humanists, we want to be more than users. You want to be part of creating these tools and also contemplating about it. So from your experience, do you see that people with humanities education can be part of this process, give some input to it, and be competent participants of the discussion? What are the roles in which humanities people or social scientists are taking part in this NLP development? Thanks.
Yeah, that's a tough one, huh? When I started working on language technology, it was around the topic modeling trend. Everyone was doing topic modeling. Everyone was using Mallet and things like that. And I got really interested into the way they were working with the technology. And that spiraled out of control. I'm right now working purely in NLP because one thing took me to the other thing, right? I was discovering, I work in Hispanic studies, so models did not exist for Spanish. So I need to create my own things, and then I realized that this thing depends on these other syntactic parser. Oh, syntactic parser for Spanish don't work very well. I need to create my own model. Oh, the model relies on an actual better language model in general. I need to create a language model. Oh, to create a language model, I need to create a better data set. Oh, the data set needs to be filtered and catered in a different way. So at some point, I wake up a morning, I was developing language models, pure language models. But the questions that I had before are still relevant, right? So when I was working with Word2Vec, I realized that the biases encoded in the English Word2Vec models were not applicable for other languages or for Spanish or even for the same period. I was working with Spanish Golden Age, which is 16th, 17th, and 18th century, and it was of no use for me to have anachronisms like watches and screens and things like that encoded in my vocabulary, because that was very limiting for the kind of lexica that I have in my own studies. So I think that we need, as humanists, we need to realize that all of these technologies, okay, I think I'm going to say that they obey commercial purposes. They are developed to facilitate some kind of increase in their commercial value. We as humanists do not really care that much about that. Maybe we should care a little bit more. But we have the duty to take that technology, question it, interrogate it, and adapt it to our own needs. And that's going to depend a lot on the different fields we work on every day, I think. I don't know if I answered your question.
Thank you for that. If I might add, and so this probably be either the last question or one before the last, so think carefully about the last question. So at the National Library of Latvia, we also have been getting us prepared for large language models, and both for using them or being a part of the process of developing the large language model for Latvian language. And I can relate to what Harold said. Can we be a part? What's our role there? But we decided that we want to be a part, so we can be more certain that the result will be something we are interested in, and not only will answer the commercial needs. So we want to be a part of this process, at least if it's only a role of being consulted, Okay. But as a National Library of Latvia, we are thinking about being a part of creating a model, and in that sense, I wanted to ask you what was your process in working with optically recognized materials, because we know that they have errors. Did you use this type of material, and if you did you try to improve the data quality before giving this data to the training?
Yes. I think that the role of national libraries is critical, because we are the ones that know our collections better than anyone else. We had many requests for our own data, the internal part that we cannot share. And at some point there was an agreement between different organizations so they could use the part of the data that was somehow protected, and they could also train models on that. But they don't know the idiosyncrasies embedded in those collections. They don't know how to properly use the data. They don't know how to read MARC. They don't know how to process ALTO files. What they want is a data set in text format that is already clean, usable, you feed it, you train it, right? And that's not what we have in national libraries. We might have scanned the collection, but that's not the same form or shape people in NLP are expecting. So I think it's our duty to be an integral part of that process, because we can inform how to properly transform our collection into something that is usable for training. And we are the only ones really capable of doing that. Talking about OCR, for example, we could not use around 40% of the OCR materials we had. We have to reject it because of bad OCR quality. Even after re-OCRing, we still have to reject 40% of the data. And the problem with rejecting is that you rely on the very technology to tell you if you should trust it or not. It's impossible to analyze manually 600,000 books that have been OCR. It's impossible. So we are in a crossroad here, but I still think that we should be an integral part of the whole process.
More question?
I'm sorry. I have raised the hand sometime.
I have a follow-up comment and question. So in this business of generative LLMs, on the one end, there is pre-training of foundational models. Then on the very other end, there is using existing models with this RAG technique, retrieval augmented generation, for instance. And then somewhere in between, there is this continued pre-training and fine-tuning for specific tasks, like you mentioned, this title generation. Mm-hmm. And it's very obvious that national libraries are at least stakeholders in this whole business, if not training themselves, like you are doing. And then this bias, as you also mentioned, is very important, because the libraries are those that can bias those models towards national, cultural, historical perspectives. But then apart from such very straightforward language models for language understanding, like the bird family, where there are very straightforward use cases for libraries and for everyone else, and apart from research, as you said, well, in research it's often the case, then we train the model and throw it away because it becomes outdated the very next day. But are there some actual use cases already, for instance, at the National Library of Norway, where you are actually using those generative language models, not for language understanding, but for generation, and using your own in-house trained models instead of using existing models like the new Llama 3 family, with applying some RAG method or something else?
Yeah, the short answer is no. We do have models trained. For example, the doc-to-vec model for the books. We have a round model for the images. We are now in the process of creating a CLIP model, which combines both modalities into one single model. So you can, for example, ask the collection, give me pictures of kids playing in the snow, and then semantically translate that into the same space and give you images depicting that very same thing. But we are now using existing models. Two reasons for that. The first one is that we're only 4 people, so we can only do so much. But the most important one really is that we are, in the AI lab, we are a test bed. We show what's possible, but it's not our responsibility to make those deployments. Right? For example, we did this development for the Sami bibliographers, which is using a language model. Actually, we use NDBird, but even though we thought it was going to make their lives easier, they ended up not using the system. They rather stuck with their own ways of doing the same thing. So integrating this technology in a library context, you need to be aware of what you are doing. If the process is somehow disrupting their day-to-day work, chances are it's not going to work. If the idea did not generate from them, it's almost guaranteed that they're not going to use the technology you have developed. Another example we have. We bundle, I can show you that real quick. Sorry, it says like 1,000 slides. Here. When we scan newspapers, we bundle them together, right? And then when we need to process each of them individually, we need to find the front page of each of them. Right now, there is a person sitting on a desk pointing on which of the images are the front page images, so we can split them apart. So we developed a model to do that job, so they don't have to have that person highly skilled doing this tedious thing. We developed a model which was very good, like 99-point-something% good. And then we say, okay, the model is done. Now we hand this to the text team. It was their responsibility to do the deployment of this thing. The problem is that even though the model that we created was good, it was fast, kind of fast, it was one step more than they were used to. So that's the only reason they're not using this system. It's taking maybe 2 seconds. They don't want to sit there waiting 2 seconds for a suggestion when they can already click. And it's an extra step for them. So developing this technology only works when you make it absolutely invisible, like in Magen, like the recommender system we have. And for RAG system, we have experimented with RAG system. We don't really see the value of RAG systems right now. We had a pilot called Talk to a Book. You select a book, we automatically RAG the whole thing. But books might not be as literal as a news article. So the kind of questions you make to a book are not the kind of questions, the factual questions you make to news articles, for example. So it's hard to get good answers on text analysis, for example, for RAG systems. So yeah, there are use cases, but at this point, I think we have advanced the language modeling part a bit more than we are so far ready to digest internally.
I will just comment that there are like two ways how you would like to implement large language models. One is directed towards the employees of the library and the workflows we have, and another is directed towards our end users, our customers. And I think it's the most popular dream in the libraries see now that we would have something like ChatGPT implemented in the digital library environment, where you could ask questions, prompts, asking for answers that are somewhere in the books of our libraries, because ChatGPT or Gemini and none of the other models know what is in Latvian books now. And we are not very eager to give this information to ChatGPT. We want to have for ourselves, maybe. But let's see, maybe we will get it in other way. But yeah, like, let's do a summary about what's in this book, or answer a question and give a list of references, summarize something. This is something we dream about. I think if we had this, nobody would object. Everyone would use it, our end users and librarians as well. But we're not there yet, and the question is how much it would cost. Would it be cheaper to buy the product for Gemini or ChatGPT, or create something in-house on national level? And again, this is the only time this year when we were exploring the costs of creating a large language model, so to do our own estimate. When looking at the papers, you also mentioned like, about colossal corpus, and then this comparison, how your BERT was compared to GPT and other models. I was wishing to have a financial estimate at the end of the academic paper. It was the only time when I was looking for something like that, and it also is a symptom that is a little bit different to compare to anything else we have done before. We never asked, well, how much should it cost for you to do such and such? But nowadays, like, how much? Yes, and do you know how much it would cost to implement our dream service at the digital library? It is indeed my last question. Provocative, maybe?
No, I don't know how much it costs to implement your digital dream in the library. But I can tell you that for this MIMIR project that I talked about at the end, we are doing an economic analysis of the whole thing, but not only including the actual training compute, which is the biggest chunk of the budget, but also the different developments in-house in each of the institutions, because that's also cost, the electricity, and the people cost as well. Hopefully we can publish the report early, well, not early September, but at some point in the fall. It's hard to answer.
Thank you so much, and give another round of applause.
Thank you.
And I hope to see you again tomorrow. Until then, no.